Hi, welcome to Chapter 20, Electrochemistry Overview Part 2. Part 1 we covered over the summer. So in Part 2 we're going to talk about voltaic cells, cell potentials under standard conditions. So voltaic cells, in a spontaneous oxidation-reduction reaction, electrons are transferred and energy is being released. The energy can do work if the electrons flow through an external device. In this case, it's flowing through a multimeter and it's measuring the voltage. This is what is called a voltaic cell. In a voltaic cell, you have oxidation occurring and reduction. Oxidation occurs at the anode, and an easy way to remember that is both words start with a vowel, oxidation and anode. The reduction occurs at the cathode, and both of them start with a consonant, not a vowel. When electrons flow, charges aren't balanced. So in order to keep the charges balanced in your electrochemical cell or voltaic cell, you need something called a salt bridge. And your salt bridge just allows the charge to be kept balanced. So it is used to keep the charge balanced. In your voltaic cell, your cations are going to move towards the cathode, and your anions are going to move towards the anode. So your electrons will flow from the anode to the cathode. So you see here's your electrons flowing. Here is your anode, flowing through your device, going to your cathode. Okay, as your electrons come into this copper plate here, the copper ions in solution will combine with these electrons and make copper. So over time, this cathode will get fatter, and this cathode will kind of get skinnier. So the mass of the cathode over here increases, the mass of the anode decreases. So again, in the cell, the electrons leave the anode and they flow through a wire or a voltmeter to the cathode. Cations are formed in the anode compartment. As the electrons reach the cathode, the cations in the solution will come over here, react with the electrons, and then deposit a metal on the cathode. The cathode gains the electrons and are deposited on the cathode. So you see here, okay, here you have the electrons, and the positive ions in solution will come and join with them. And over time, this cathode is going to get larger and larger. This one is losing the electrons, so the zinc ions are going into solution, so this anode is going to get smaller and smaller. So your anode will lose mass, but your cathode will gain mass. So the electromotive force, or EMS, of a voltaic cell is kind of like a waterfall. Okay, water spontaneously flows one way, from the high point to the low point. A direct comparison is electrons will flow spontaneously one way in a redox reaction, from the high to low potential energy. And in that case, it's always going to flow from the anode to the cathode. So you see here's your anode, and it's going to flow to your cathode. Your anode will have the high potential energy, and your cathode will have the low potential energy. The potential energy difference between the anode and the cathode is what we call our electromotive force, EMF. It's also known as cell potential, and we abbreviate it E cell. And the E cell is measured in volts, and a volt is 1 joule per coulomb. So here is a table of some standard reduction potentials. So reduction potentials, or we call them half-cell potentials, for many electrodes have been measured and tabulated. That's what's shown here. The values are compared to the reduction of hydrogen as a standard. Your standard conditions are the same as they were in Chapter 19. For concentrations, it's 1 molar. For gases, it's 1 atmosphere, and the temperature is 25 degrees Celsius. Whenever an electric potential is assigned to a half reaction, the reaction is written as a reduction. So all of these are written as reductions. You see here, reduction, half reactions. The more positive the reduction potential, the greater the tendency for reduction to occur. So here, more likely to have reduction. Here, not so likely. So the more positive, the more likely it is to reduce. Remember, reduction is gaining electrons. So how does stoichiometry affect our standard reduction potential? Well, if you increase the amount of substance in a redox reaction, both the energy, which is measured in joules, and the charge, which is measured in coulombs, will increase. But if you take the ratio of the two, joules divided by coulombs, remember that is what we call our volts, that will remain constant. So because of that, changing the stoichiometry coefficients in your half reaction does not affect the standard reduction potentials. Standard reduction potentials are intensive properties. So how do they kind of measure these? Well, you have to start with a standard. And the standard is your standard hydrogen electrode, or SHE, standard hydrogen electrode. By definition, as the standard reduction potential for hydrogen, they say it's 0 volts. So how do we calculate our standard cell potential? The cell potential at standard conditions can be found through this equation right here, where you take your reduction potential of your cathode minus your reduction potential of the anode. So remember, at the cathode, you're going to have reduction occurring. At the anode, you have oxidation occurring. Because cell potential is based on potential energy per unit charge, it is an intensive property. So that's what we were saying before. It doesn't matter what the stoichiometry coefficients are. So how do we calculate this? Well, say we have our cell, which is shown here in this diagram, and our anode has a potential of negative 0.76 volts, and the cathode is positive 0.34 volts. So remember, our equation is the cathode minus the anode. So you would take 0.34 minus a negative 0.76, and you would get your reduction potential for this cell is 1.10 volts. And that's what's shown here. Okay, another way to look at it is if you draw this arrow going to the more negative, your anode would always be on top, and then your cathode, and this distance here is the potential of your cell. So the reduction potential for reactions at the cathode is more positive than the reduction potential for the reactions at the anode. So your electrons are going to flow spontaneously through an external circuit from the electrode with the more negative value. So that's your anode, to the electron with the more positive, and that's your cathode. So the greater the distance between these two voltages, the greater the voltage of the cell. So here's the same cell over here, another diagram. And it's saying for the oxidation in this cell, you're going to get your reduction potential as negative 0.76. For the reduction reaction, you're going to get a plus 0.34. When you plug it in, you're going to get 1.10 volts. So which of the reactions here, which of these two reactions, is oxidation? So remember, oxidation is losing electrons, and reduction is gaining If you remember oil rig, that will come in handy. So which reaction is losing electrons? Well, it looks like the zinc reaction because the electrons are products. So that is what zinc is oxidizing, and it has a E naught reduction of negative. I forgot the negative sign. And copper is gaining electrons. So it is reducing. So it has a E So remember, wherever the reduction is, that is your cathode. Wherever the oxidation is, that is your anode. And your formula is cathode minus anode, so it'll be 0.34 minus a negative 0.76, so they end up adding to each other. So for your zinc copper ion voltaic cell, the reaction shown below. Given the standard reduction potential for zinc is negative, so we have our E reduction for zinc is equal to negative 0.76. What is E reduction for copper? So again, you got to figure out, remember our formula. So E of the cell is equal to E reduction of the anode minus the cathode. Let me just go back and check that I said that right. Oh no, I didn't. Look at that. I knew I was doing something wrong. So let's see, reset. It's E of the cathode minus E of the anode. Sorry about that. So remember, your anode is what gets oxidized, oxidation, and your cathode is reduction. So let's look here. Zinc goes from 0 to a +2. So that is getting oxidized. So that is the anode. And this one here is the cathode. So now they told us zinc is negative 0.76, and that's our anode. So we could get our E cell, E reduction of our cathode is what we're looking for, minus a negative 0.76. So then that becomes positive, and then you bring it over, it subtracts, and you're going to get E reduction is going to be 0.34 volts. And this is for the cathode. So how does oxidizing and reducing agents work? So remember from the summer, the agents, so if you have a oxidizing agent, it is the substance that gets reduced. And if you have a reducing agent, it is the substance that gets oxidized. Because agent means to do. So what does oxidizing? The reducing agent, the element that reduces. What will cause something to be reduced? The one that's being oxidized. Okay? So the more positive the value of your E reduction, the greater the tendency for a reduction to happen. So here we have our substance that will reduce very easily. If it reduces very easily, it is a strong oxidizing agent. So as you go up, you become a stronger oxidizing agent. Down here, a terrible oxidizing agent. It's a weak oxidizing agent. Okay? The stronger the oxidizer, so oxidizer is another way of saying oxidizing agent. And this would be reducer. The stronger the oxidizers have the most positive reduction potentials. The strongest reducers have the most negative reduction potential. So let's look at the blue side here. It says increasing strength of reducing agents as you go down. So over here you have a strong reducing agent. And here you have a weak reducing agent. And that is the end of part 2.